In today's lecture, we will discuss the distribution of particles in two equal sized compartments. Now, first one is the distribution of one particle in two compartments. Suppose an open box is divided into two equal sized compartments by means of partition as shown in table. Let the particle be thrown into the box from a certain distance. So the particle is equal likely to fall into any one of the two compartments because there is no reason why the particle should prefer any one of the compartment over the other. Let us denote the particle by A. Then the possible arrangements of the for distributing the particles in two compartments are the particle A in the first compartment, then the second compartment will remain empty, and the particle is in the second compartment, then the compartment 1 will remain the empty. So in this way we can distribute one particle in two compartments. Is the distribution of two particles in two equal size compartments. Now in this case we throw two particles in a box divided into two equal size compartments and see in the table how they are distributed. First of all, in compartment 1, if they are both A and B particle in the compartment 1, then the compartment 2 will remain empty. And the second is the if particle A is in the compartment 1, then the B particle will be in the compartment 2. And third possibility, if the compartment if B particle is in the compartment 1, then the A particle should be in the compartment 2. And fourth is compartment 1 is empty and both particles are in the compartment 2. So in this way we can arrange the two particles in two equal sized compartments. But conclude there are 4 means 2 raised to power 2. Here this 2 denotes the compartments and this 2 denotes the number of particles. Therefore 2 raised to power 2 means 4. There are 4 distinct arrangements for distributing two particles in two compartments. Now next is distribution of 3 particles in two equal sized compartments. This is the way how we can arrange the 3 particles in two equal sized compartments. If the 3 particles, that is A, B, C, are in the compartment 1, then the compartment 2 will remain empty. Now next distribution we can do in a orderly manner. What orderly manner? AB in first compartment and C in the second compartment. Then we go further, BC in the first compartment and A is the second compartment. Then further CA in the first compartment and B is in the second compartment. Now we will interchange the particles of compartment 2 in compartment 1 and in compartment 1 into compartment 2, that we interchange the particles. And last one is compartment 1 is empty and all 3 particles in the compartment 2. So in this way we can arrange the 3 particles in two equal size compartment. So here also there are 8 distinct arrangement, that is 2 raised to power 3. 2 is compartment and 3 is the number of particles. Distinct arrangement for distributing 3 particles in two compartments. Here in general way we can say that if we have to arrange n particles in two equal size compartments, then the number of arrangement should be 2 raised to power n. In a generalized case 2 raised to power n, n is the number of particles. So from here we can calculate how much arrangements can be made. If there are 3 compartments, then 2 is replaced by 3. If there are 4 compartments, then the 2 is replaced by 4 compartments. So this is the method how we can calculate the number of distinct arrangement for distributing n particles in n compartments, that is n raised to power n. Now next, what are microstates and macrostates of a system of particles? First one is microstate. It is the distinct arrangement of particles of a system. As an example, If 3 distinguishable particles are distributed in 2 compartments, then 8 distinct arrangements are possible. How? In this way. This one is also we discussed in the previous slide, how we can arrange 3 particles in 2 compartments. So the total number of arrangements are 8. Next, macrostate. The arrangement of the particles of a system without distinguishing them from one another. Then that arrangement is called the macrostate. For example, if 3 indistinguishable particles are distributed in 2 compartments, then there are only 4 distinct arrangements are possible. How? We can see the table. Here these 3 are indistinguishable particles. That is, first particle is A, second is A, and third is also A. That is indistinguishable particles. Then how we can arrange? In one compartment, if 3 particles are there, then second compartment is empty. Second option, in the first compartment there are 2 particles, the second is compartment is 1 particle. In the first compartment is 1 particle, then in second compartment there are 2 particles. And last one is the, if first compartment is empty, then the all 3 particles are in the second compartment. So in this way we can arrange 3 indistinguishable particles in 2 compartments. Now next, here we can arrange 4 particles in 2 compartments. How we can arrange 4 particles in 2 compartments? This is shown in the tabular form. First, in the first compartment, if the all particles are distinguishable, that is, particle is A, B, C and D, means they are distinguishable particle. If first, in the first compartment, if the particles are A, B, C and D, and the second one is the empty, then macrostate, in the first there are 4 particles, then here is 4. In the second compartment there is no particle, so that's why this is 0. And frequency is, because this is 1 time, so that's why the frequency is 1. Then the probability is the 1, means microstate, divided by 16. 16 means total number of trials. Total number of trials are 16. That's why probability of this is frequency 1 and 1 over 16. Now second one, how we can arrange? This is also in the orderly manner. That is A, B, C and D. First one, then B, C, D, A, then C, D, A, B, then D, A, B, C. This is the way how we can arrange the particle. That in first compartment there are 3 particles, and in the second compartment there are 1 particle. So this is we can arrange in a orderly, simplified manner. So macrostate, in the first compartment there are 3 particles in each. That's why this is 3, and in the second there is only 1 particle, then there is 1, 3 and 2, 3 and 1. Then the frequency, first, second, third and fourth, there are 4 times. That's why the frequency is 4 and the probability is 4 over 16. Now if we arrange in first 2 particles in first compartment and other 2 are in the second compartment, then this is the way how we can arrange the 2 particles in first compartment and other 2 particles in the second compartment. It is also simplified manner, A, B, C, D, C, D, A, B. And the macrostate, first compartment the particles are 2, and then the second compartment the particles 2. Therefore the macrostate is 2 and 2, 2. And the frequency is 1, 2, 3, 4, 5 and 6. Therefore the frequency is the 6. That is, the microstates are 6 microstates. Therefore the probability is 6 over 16. Now next we can interchange the particles into the compartments. That is, in the second compartment the elements of second compartment particles are changed into the first compartment, and the first compartment elements are changed into the second compartment. So the frequency is also changed. That is first one is macrostate, that is and the particles are 1, that is 1, and second compartment the particle 3, 3. That is reciprocal to this case, that is 3, 1. In this case is 1, 3. But the frequency, that is number of microstate, remains same, that is 4. and the probability also remains same, that is 4/16. And the last way is the first compartment is empty, and in the second compartment there are 4 particles. So the frequency is 0, 4, that is the reverse of first, that is 4, 0, this is 0, 4, and the frequency is 1, and the frequency is so the probability is 1/16. So in this way we can arrange the 4 distinguishable particles in 2 compartments. Next, if particles are indistinguishable, then what to do? This is the way how we can arrange the 4 indistinguishable particles in 2 compartments. That is the first particle A. That means they are indistinguishable. So we can arrange first 4 particles in one compartment and second compartment is empty. So the number of microstate frequency is 1 and macrostate is 40. Second case is compartment 1, the particles are A in the first compartment, and the second compartment is only A, then the macrostate is 31, and the second in the first compartment 2 particles A and the compartment 2 is also A, then the macrostate is 2 and 2. Similarly, now we can reverse the order, A, and then last one is the first compartment is empty and all 4 are in the second compartment. So this is the case for indistinguishable particles. Now next we can see that the number of microstates depends upon whether the particles are distinguishable or indistinguishable. That is the number of microstates depend mainly the particles are distinguishable or indistinguishable. How? For example, the macrostate 31 has 4 microstates, as we see in the previous slide, if particles are distinguishable. But in this case, if the particles are indistinguishable, then the number of microstates for 31 macrostate is 1. Then there is only 1 microstate if the particles are indistinguishable, while if the particles are distinguishable, then there are 4 microstates. Therefore, the main conclusion is the number of microstates depends upon whether the particles are distinguishable or indistinguishable. Now next, what is the relation between thermodynamic probability and the probability of macro and microstates? Now a priori probability is given by, it is as we discussed in our earlier lectures, that is equal to the 1 over total number of microstates of the system. Now what is the probability of macrostate? It is the ratio of number of microstates in the given macrostate to the total number of microstates of the system. But as we know that the number of microstates in the given macrostate is the thermodynamic probability, therefore we can write P is equal to, that is probability of macrostate is equal to thermodynamic probability divided by total number of microstates of the system. Now from equation 1 and equation 2, but we conclude that the probability of macrostate is equal to the thermodynamic probability multiplied by the probability of the microstate. So this is the relation between the thermodynamic probability and probability of macro and microstates. Next, what is the effect of constraint on the system? Now what are constraint? Basically constraint is a set of conditions that must be obeyed by a system, For example, let we want to distribute 3 particles in 2 compartments, then the table is given by. Here we can see that the macrostate is 3, 0, then the microstates are A, B, C in the first compartment and second is empty, and for macrostate 2, 1, the 2 particles are in the first compartment and the 1 particle is in the second compartment, then the number of microstates are 3. Similarly, for 1, 2 macrostate, the microstates are 3 and the particles are first in the first compartment and 2 particles are in the second compartment. And for macrostate 03, the first compartment is empty, and in the second compartment there are 3 particles. So the number of microstates is 1. Now what are the effect of constraint? Let us see. We put a constraint that no compartment should remain empty. This is the constraint that no compartment should remain empty. Then we see that in the macrostate 30, the second compartment is empty, and in the macrostate 03, the first compartment is empty. So this constraint, which no compartment should remain empty, then the macrostates 30 and 03 cannot exist. So the system can have only 2 macrostates, that is 2 1 and 1 2. So 2 1 has 3 microstates and 1 2 has also 3 microstates. So the total number of microstates are 3 plus 3 6. So for this constraint that no compartment should remain empty, we have 2 macrostates and 6 microstates. Now second constraint, the particles are indistinguishable, that is all particles are same, that is first particle A, second is A, the third is also A. Then what is the effect on the distribution if the particles are distinguishable? Then in such a case we have 4 macrostates, that is 30, 21, 12 and 03. We have 4 macrostates, and each macrostate will have only 1 microstate because the particles are indistinguishable, means A. Then this is possibility is 1, then for A and A, so this is only 1 because they are all same, because the particles is A. So for this all 3 are same, that is the number of microstate is 1. For this also microstate is 1, and for this also the microstate is 1. So we can say that if we put a constraint that the particles are indistinguishable, then the total number of microstates will be reduced to 4, that is 1 plus 1 plus 1 plus 1, that is 4. So we can see that how the effect of constraint on the system, that is constraints may affect the number of microstates for a given system. Now dear students, I have given you exercise in this lecture. Write in the tabular form the distribution of 3 particles in 3 compartments for distinguishable particles as well as indistinguishable particles. So write down the table in the similar way as we have distributed 2 particles in 2 compartments, 3 particles in 2 compartments, and also 4 particles in 2 compartments for distinguishable as well as for indistinguishable particles. In a similar way you can also distribute 3 particles in 3 compartments. So this is your exercise. So complete your exercise. If you have any problems, kindly let me know. So this is all about today's lecture, and meet you in the next lecture.